Today I'm going to talk about the research of my lab in the intersection of machine learning and healthcare, more specifically medical imaging, where we view the insight from the clinicians as a driving force for research, as we basically view it as a bridge that inform us, and the interaction between us, between us as a computer scientist, an engineer, and clinician can inform each other and brings new problem, hence the title of the bridge. So, as many of you know, that AI is increasingly adopted by clinical workflow. One of the driving forces is increasing the cost of healthcare. This plot shows increase of the cost of the healthcare from 1970, that even after correcting for inflation, it has increased six-fold increase. So adoption of the AI in medicine hopefully eventually result in more efficient workflow, and also for patient in terms of receiving personalized healthcare. So if you consider the application of machine learning in healthcare as one line, that one end of that is clinical practice, the other end of that is medical research, AI has found application almost everywhere, all the way from helping clinicians and radiologists to read the images faster, to finding optimal embryo, all the way to medical research, probably with all of these news that you hear about drug development. Throughout this spectrum, there are many challenges and, of course, opportunities for contribution for people like us. In my opinion, four of the main challenges are: one is multimodality. Decision-making in clinic is always multimodal. A clinician looks into an array of information from lab tests, images, EHR to make a decision. Developing method that can consume all of this information in an efficient manner is an important direction of research on its own. We are increasingly using models that are complicated. It is important to be able to explain those, not only to gain a trust, but in order to also understand the underlying biases that might be hidden in our data or our models. We are using the data set that by design is quite expensive. We should be able to incorporate knowledge in order to gain data efficiency and take the best advantage of this data. And finally, if you are interested in incorporating this research into medical research, we have to go beyond prediction toward incorporating causal inference. So when talking about the future of AI, many people want to compare that with self-driving car, mostly from the point of view of importance of the safety. In my opinion, the application of AI in healthcare is more like a autopilot in commercial airplane, and the difference is that the ultimate goal of the self-driving car is to remove the driver, while we have to keep the clinician in a loop. So I think eventually we are going to converge to a point that we have to keep a clinician in the loop, and our system works like a autopilot. And throughout this talk, I hope that convince my audience that having this feedback with clinician brings new insight, perhaps improves the performance of our algorithm, but also bring new problem that we did not know that even exist. So throughout this talk, I'm going to talk about two directions. One is about how this kind of interaction can bring data efficiency in the context of learning and also statistical inference. And the second direction, second part of my talk is about model explainability. So let me get started about the first part of the talk. This is the work done in collaboration with my colleagues Kun Zhang from CMU, my former postdoc Mingming Gong, who's now in the stat department in Australia, and two of my students, and also thanks to a funding agency that supported us throughout this process. So let me motivate this problem in the context of a specific disease called chronic obstructive pulmonary disease, COPD. It's one of the leading causes of the death worldwide, and the symptom includes shortness of the breath, cough, and sputum. And there are multiple factors. Smoking is one factor, pollution is another factor, but also there is an important genetic and gene environment interaction aspect to this. So the way that the COPD is diagnosed is through a machine called spirometers that the patient is asked to inhale and exhale air through that. And this machine measures amount and speed of the air that the patient exhales. So one of the metrics that is usually looked into is called forced expiratory volume in 1 second, that patient have to inhale and forcefully exhale his lung within 1 second, and then the amount basically represent how much obstruction or destruction of the tissue or change in the biomechanic of the lung contribute to the shortness of the breath. So this is called FEV1. I'm going to refer to that several times throughout the talk. So there are multiple processes involved in COPD. Two of the major one is so-called emphysema, which is destruction of the air sacs. And the second one is inflammation in the airways. But spirometry metrics is aggregate measure that does not distinguish the contribution of the multiple process. And as a result, increasingly CT images of the lung are looked into because it directly measures the anatomy. COPD is highly heterogeneous. Just talking about emphysema, there are multiple subtypes of the emphysema that are contributing to disease. Sometimes this destruction of the tissue happens close to airway, sometimes it's broad area, sometimes close to boundary of the lung. But these subtypes are visually defined. And one question that we are trying to answer is that is there any way that we can define in a data-driven manner that goes beyond the classical radiometrics that is used clinically? And second, how we can connect these to this heterogeneity to etiology of the disease. Well, talking with this audience nowadays about prevalence of the machine learning, perhaps one of the ideas that comes to mind is that why not, for example, using CT scan of the lung and build some supervised model to predict for example, a spirometry FEV1, with the hope that this representation is learned by the model are quite informative. And in fact, building such a model is possible. Us and many others have done that. And for example, in this graph, I'm showing you on the y-axis, the R-square of predicting FEV1. Each bar represents different method. The blue one is the method that we proposed a couple of years ago. And y-axis is the proportion of variance explained. And you see that it works pretty well. We tested it on many different metrics of the disease. But FEV1 is one of the axes of the COPD. COPD is not unidimensional measures. And one question that comes to mind is that, so how generalizable this representation or this feature that you have extracted from the image are with respect to other metrics of the disease severity? So we performed very simple experiments. We trained this model with respect to FEV1, and then we cut the last layer, so-called pre-ultimate layer, and said that, okay, can we use these imaging features that we extracted that is used from the model that is trained for FEV1 and try to predict another metric of the shortness of the breath is called MMRC dyspnea score, which is about the shortness of the breath, but it's not exactly FEV1. It's multiple factors. It's mostly like a functional measurement. And we performed this experiment. We used this last layer and used linear regression. We call it indirect approach because we are not retraining the model. And we also performed this experiment of training model again and see if how much of the gap is between these two models. And we saw that there is a significant gap between these two, which means that the model that is trained for one metric of the disease does not necessarily learn the features that are generalizable across the other metric of the disease, no matter how related they are. So the next question that comes is that, well, is it possible to construct a generalizable features that is not committed to only one metric of the disease, but simultaneously is related to many metric of disease severity, perhaps the one that we don't have in our database. And as a result, we want to see how much we can get away without the supervision. So how can we learn these features in an unsupervised fashion? If you're coming from a field of computer vision, probably, or many other fields, because this paradigm is being used many other places, one of the ideas that come to my mind is that why not using so-called self-supervised approach? The general idea of self-supervised approach is as follows. Unlike supervised method that is trained to predict one task, self-supervised approach are trained to distinguish samples from each other. There are multiple variants of the self-supervised approach. Probably one of the most common version of that so-called contrastive learning. So let me explain this in a cartoonish way in this schematic. So let's say that you want to train, let's say, a model that distinguishes animals from each other without telling the label of the image. So if I'm given an image of a dog, if I apply a set of transformation on an image that does not change the context, for example, change the color, hue a little bit and rotate it, that doesn't change the dogness, that constitutes a positive set, and a random draw from this data set gonna make a negative set. And then my goal would be to train a feature extractor such that the similarity between these positive sets are closer to each other rather than element of the positive set and negative. So that's the general idea of the self-supervised learning using contrastive learning. Now the question is that what would happen if you apply this method on a medical images? So let me give you a setup. So I can look at the area of a lung, I can change the hue and rotate it a little bit to create my positive set, and the negative set would be a random draw from the other lungs, other location in the lung to create a negative set. So if we do that, unfortunately, model will learn to cheat and use so-called shortcuts. So what are the shortcuts? Shortcuts are spurious features that are correlated with the true signal, but those are easier for model to learn. In fact, shortcuts are almost everywhere. And for example, in this example, DeGrave et al. Showed that many of the common deep learning algorithms that try to detect the presence of the COVID on the radiology images focus on marker from the hospital rather than lung itself. That is an example of the shortcut. In a study, we showed that it is not only supervised approach, but also self. We also showed in some paper that published last year that it's not just supervised approach, also self-supervised approach are quite prone to the self-supervised learning. So what would be the example of the shortcut in this setup that I mentioned earlier? In fact, if you show this to a radiologist and say that, well, let's see, how would you distinguish between this positive set and a negative set? Radiology will come back to you that anatomy is the shortcut. So effectively, if you construct your model this way, the model will learn to use the anatomy as a shortcut, which is not an interesting feature in this case, because they're all more or less coming from this. You're taking images of not a cat and dog, but all of them are images of, let's say, CT scan of the lung. So they all share similar anatomies. So subtle changes in the image is what you're interested in, not anatomy itself. Fortunately, though, because of this insight, blocking this shortcut is not difficult. We can use image registration, which is basically a procedure that makes a correspondence between location on the image and make sure that the positive sets are all coming from the same anatomy that effectively block the shortcut that I mentioned earlier. But that solves part of the problem, because in this way, we are constructing anatomically specific features while we are interested in patient-specific features. And each patient has his or her own anatomy. So what we did was that we basically used so-called graph convolutional neural network, where we viewed every patient as a graph that has his own or her own anatomy, where the nodes are anatomical landmarks, and the edges represent the vicinity of the landmark within each other that varies from patient to patient, to create a two-level self-supervised learning, that one learns anatomical features, the other one learns patient-specific representation, and the graph basically encodes the patient-specific anatomy. There are more detail into this, but let me show you some results. We evaluated this method that we train in so-called end-to-end fashion, which means that all of those parameters are learned at the same time, using 3 levels of evaluation. The first is that how well this method performs when it is compared against the supervised approach. Because the supervised, for the same target that the supervised approach is trained against. So in this case, the supervised approach should be viewed as an upper bound that you want to reach. In the second one was basically our motivation of a motivating slide that I showed you earlier, that if we can train this supervised approach, how generalizable it is to the other metrics of the disease severity that the supervised approach is not trained on. And finally, we're going to evaluate this algorithm in terms of bootstrapping for another disease, in this case COVID-19, for a smaller sample size, using the same anatomy, same modality, but different disease. So let's get started. In the first part, in the first set of experiment, I'm showing you two of the metrics here. Each of these plots, one shows FEV1, forced expiratory volume within 1 second, and the ratio of that to forced vital capacity, which are the two of the important metrics to characterize COPD. And the horizontal line is the supervised method that is directly trained on these signals. Each of these bars represent different self-supervised approach that is performed previously and applied previously on medical images. Y-axis is the variance explained, and the closer the gap, so basically in this case you have to view this horizontal line as some sort of upper bound, because the supervised approach is directly trained to predict these two metrics. Now, as you see, so what we want is that we want to close this gap between supervised approach and self-supervised approach. The take-home message from this plot is that incorporating this idea by blocking shortcuts and constructing patient-specific representation help us to bring the gap closer. But what would happen when we want to predict other metrics of the disease severity that the supervised approach is not trained on? In this case, horizontal line is no longer an upper bound. And the bigger the gap between the supervised approach and self-supervised approach is better. The take-home message from this graph is that almost all of the self-supervised approach surpass the supervised method. And the method on the last one, the pink method, which is the method that we propose here, it has the slightly bigger gap with respect to others, suggesting that incorporating the shortcuts can learn more generalizable information. We also try to see how we can use this data to bootstrap small sample regime. In this case, for COVID-19, we are using same anatomy still. We are talking about anatomy of the lung, and the data modality is the same because the CT scan of the lung, but the data set in this case is small, it's only 1,100. So this is the data set that's collected from a hospital in Moscow, and the target is predicting the disease severity not only based on the reading from the CT scan of the lung, but also blood pressure, oxygen level, and many other metrics. So we performed several experiments, but the take-home message is as follows. If you train a supervised method for such a high-dimensional data, because we don't have enough samples, supervised method does not generalize very, very well. And in fact, all of the different variants of the supervised approach, self-supervised approach, surpass that is trained on COPD, which is a completely different disease, but the same anatomy and the same data modality, surpassed with a slight modification to the model. And the last three plots are three different variants of the method, which we turn on and off different components of the model. The way that we block the shortcut, the way that we make the anatomy patient-specific, and so on and so forth. And you see that in each of those, they are positively contributing to performance of the model. But we said that, okay, so it seems that the feature that we learn is generalizable. It's generalizable with many metrics of the disease severity without retraining. It can be also used to bootstrap small sample regime when the anatomy and modality is the same, although the disease is different. Can we use this information, can we use this new endophenotype to relate it to other metrics of the disease severity to shed light onto the underlying sub-processes of the disease? Yes?
I had a question about the first part.
Yes.
So, as far as I understand it, you say if you know about shortcuts, then you can block them and get better performance. What if you don't know about the shortcut?
Yes, that's a really good question. In this case, we were told what the shortcut would be. But if you don't know the shortcut, that's basically, we studied this a little bit, that even for the cases that we don't know the shortcut, there are some regularization that you can alleviate the problem. This is not in this slide. I'm happy to show it to you. but you won't be able to ever close it. That's a negative result. Okay, so if it is generalizable, can we, for example, relate this endophenotype, for example, to some blood measurements? So going back to the COPD, so we know that there are immune system involvements that are involved in the severity of the COPD. That has been studied in the past. One question that we had, is the new features that we extracted from the image as a new summarization of this data still preserve those information or not? So in this case, you can think of those as a two random variable, that X is this summarization of the images, and Y is, in this case, measurement from the blood. And we want to see how far we can go in terms of understanding how this more richer representation that we get from the images are related to this measurement from the blood. But before answering this question that how they are related, we have to answer if they are related. And when we usually ask questions like this, we have to pose this question formally in terms of hypothesis testing, that we have two variables. X is measurement, this high dimensional measurement from the images. Y is another metric, another modalities. And the null hypothesis is that these two modalities are independent from each other. So the power of such a test is the number of the patient with the both modalities. However, I'm sure many of us that have worked with the real data have seen scenarios like this, that you have a lot of samples that have only one modalities. And this is usually the data that is discarded. And in fact, this is a very common problem that also faced in the industry. This is what drive the initial part of the research by our colleagues in Pfizer, that says that is there any way that we can take advantage of this data that we usually discard? So in the following 3 slides, I'm going to give you the general idea how this data set that is usually discarded, we call them unpaired data because the other modality is missing, can help us in terms of studying these hypotheses. So this null hypothesis can be written as so basically equivalent of the following, that the joint distribution can be written as the multiplication of the marginals. And the very least that this unpaired data can help is providing better estimate of the marginal. In other words, these unpaired data can give us better control of the false positive. To give you a little bit of the detail, we extended a method that previously proposed by Gretton et al., so-called Hilbert-Schmidt independent criteria, where basically a statistic almost looked like this. I'm saying almost because there are some ugly term that is proportional with 1/n3 of the trace. I just avoided that to avoid the visual clutter in this slide. But the general idea is as follows. The statistic looks like this. It's like a trace of K matrix, that the K matrix is the patient-patient similarity using first modality, in this case imaging, and the L is a patient-patient similarity using the other modality, in this case blood samples. The solid line represents the set of patients that have pair modalities, that have both modalities, and the dashed line represents the samples that are missing modalities. It is not really difficult to see that you can rewrite this statistic with the eigenvalues of the K and L, and the general idea here is that the unpaired data can give you better estimate of eigenvalues that can be used in this case.
Is this a version of MMD?
No, it's a version of HSIC.
Oh, okay.
But MMD and HSIC are related.
They're related.
Yeah. Okay. So we also studied this a little bit further. I know that as a last talk, I'm not supposed to show you theorem, but bear with me within 30 seconds. The general idea is as follows. Basically, the first theorem says that the more unpaired that you have, you can reduce the variance of the estimation better. It means that more unpaired data help you. The second theorem is that if you're willing to make some assumption that the data set living in some manifold, your power is at least as good as HSIC. Basically, the case that you're discarding the data. That's basically the idea. It's like the rest is, forget it. It's unimportant. Okay, so we evaluated, yes?
Are you assuming
You see at random. Yeah. Yes.
Why don't you guys use a domain transfer technique?
Yeah. Okay, that's a good question. So if you're doing domain transfer technique, so let's say that you, first of all, you have completely two different modalities. Like, let's say one of them is the tabular data, the other one is imaging data. Let's consider you want to do something like you can make the tabulated data into discrete case that you can do something like a cycle GAN. It's the equivalent of generating data. It's an overkill to answer simple statistical test because you will be at the mercy of the, so you're effectively doing data imputation. So in this case, so what we are saying is that if you want to answer two samples are related or not, impute the statistic. Don't impute the data.
Okay, but I mean,
It's much easier problem.
generate data so you can give you some variance, right?
Yeah, sure. I mean, like if it is possible. Okay, so we perform several simulations. The first simulation, in the first set of simulation, we are assuming that two modalities are not dependent on each other. In this case, we are going to look into false positive rate. In the second scenario, we are assuming that two modalities are related to each other following the assumption that we have is a low-dimensional manifold. So let's take a look. The y-axis shows the type 1 error, and the horizontal line is a 5% nominal value that we typically use for rejection of the null hypothesis. And the x-axis represents the number of unpaired data that we are using to add to this test. The blue line represents the method that discards the data. So as you add more data, the behavior of that does not change. We presented two variants of our methods. That basically these two variants, one of them is more like the regression that we do in the heritability analysis, that x is not random, y is random. And the second variant, they're both random. That's two variants. And what this plot shows is that by adding more unpaired data set, both methods hover around the nominal value for rejecting null hypothesis. Means that by adding more unpaired data, you're not inflating the statistic. Under the second scenario, the two modalities are related, so we have to look into the power. Again, y-axis is the power, x-axis is the number of unpaired data set. And the blue represents the method that discards the unpaired data. Again, by adding unpaired data, behavior does not change. And the best that you can possibly achieve is that the oracle shows you the data. That's kind of like an upper bound. And the two variants of our method is here filling the gap between discarding the data and the oracle. That's the best that you can possibly achieve. Going back to our problem, we had thousands of each modalities, but only a small subset of modalities that have both blood samples and imaging data. And then that was part of motivation. And based on the previous study that we know that the immune system are involved in this disease. So as a result, we know that the null hypothesis should be rejected. So we are looking into minus log p-value by adding more unpaired data set. And we see that if we are discarding all of these unpaired data set, the study is underpowered while by adding more unpaired data set in this case, they eventually reach a significant level. So where are we going with this? This is the ongoing research. As I mentioned earlier, this slide is about ongoing research. We want to explain this heterogeneity of the disease. So we create a joint embedding between imaging and the gene expression. The detail of that is unimportant, but we are able to place each of these patients in so-called two axes of the disease. Here, each dot represents one patient, and the color represents FEV1. The darker the color, the more severe the case. So let me showcase three examples. They're all doing really bad in FEV1. These are the three examples of the patients that are all doing very bad. And this is a sagittal slice from the lung of these three patients. They're all doing very bad in FEV1. When we show it to our clinician and then show the corresponding the clinical metrics of these, and a couple of examples like this. He gave us this example. Anybody here attended medical school and is familiar with the term pink puffer and blue blower? Okay, no medical school. Okay, so basically pink puffers, it's a stereotype of the patient. These are the patients that are usually older, their skin become pinkish. And these are the patient has a wheezing sound when they are breathing, and they tend to have a lower BMI. They lose, they look very thin. And the blue puffer again is a stereotype. Is based on the phenotypic understanding. Is basically the color of the skin become a little bit bluish, and these are the patient that has a lot of sputum and tend to be obese. So it seems that by combining this imaging and genetic information, we are able to create these two axes of the disease where each patient has a coordinating, and give basically without even looking at the representation of the patient in the clinic, provide some evidence to what clinically believed to be two subtypes of the disease. So we are very interested in studying it further, and this is the paper that we are going to submit in the following weeks. So to summarize the first part of the talk was about gaining data efficiency for learning, using insight from clinicians to improve performance, and in this specific case, blocking the shortcut that result in a method that train very generalizable features that can be used for many other metrics, many other tasks. In the second part of the talk was about gaining data efficiency in inference, that we can take advantage of the data set, most of the time very expensive data set that we typically discard. If there's any question, I'm happy to answer. If not, I'm going to switch the gear and talk about the second part of my talk. Okay, so let me switch a gear, and this is the second part of the talk where I focus on explainability of models like this. So this is the work that is done by my student Sumedha Singla and my former postdoc Brian Pollack in collaboration with our colleagues in the radiology department, Stephen Wallace, and our HCI colleague in CMU, Motahar Islami. Okay, so perhaps one of the most common metrics of explainability in computer vision are methods such as GradCam. That these methods basically tells you which areas, for example, in image, let's say that if you are trained and modeled to say cat and dog from the image, basically create a heat map that says which areas of the image are contributing the most in the prediction of the model. However, application of this kind of approach for medical images, as Raj alluded to yesterday, are quite problematic. For example, sometimes the abnormality is supposed to be very localized, in this case lesion, while heat map is all over the places. Sometimes two different abnormalities result in relatively similar heat maps that leaves the interpretation of the model to the imagination of the users. And this is quite problematic. In fact, every time that we showed it to our radiologist, he said that, get this heat map off the image, I want to see what's in the image. And he always come back with the same question. What should change in the image so that the decision of your deep learning method switches? And what he said basically made us think deeper, a little bit deeper about this notion of explainability. So what he was interested in was not in a where question, not where in the image are contributing, but while he was more interested in why question. In fact, he was more interested into seeing some sort of a counterfactual world where some changes in the image result in different outcome. So we thought about like, what if we can create some sort of like, if for example, if we have an image and this, let's say neural network that I'm showing here as a black box, create some value of the probability of the, let's say an outcome. What if we provide some sort of a knob that start from factual output, factually put the output of the original image when it's inputted in, and it can play with this knob and move it by some delta. And our job would be to create some sort of like explainer that this explainer create a new image where if you plug in back that new image, it's going to create that counterfactual desirable outcome. So it effectively is like a knob that exaggerate or de-exaggerate the effect of the disease. So, so we thought about like what would be the criteria for designing this model. The output should look realistic because we want to communicate that to our radiologists. Should be compatible with Blackbox, so that if we play with this knob and create a new image, the output should follow the knob accordingly, and it should be self-consistent, meaning that if you create a new image that is delta perturbed and you want to apply the same experiment on this new image and bring it back, you should create the same image. That's basically the criteria. I won't go through the detail how this is done, but effectively is a conditional generator. It's a conditional generator that divide the output space of the probabilities into quantiles and generate a sample from that quantiles. So, but what about the evaluation? I think for explainability, the issue, as Raj yesterday mentioned, is an evaluation. So first I'm going to show you some visual evaluation and tell you that how we went ahead and applied different approaches for quantitative evaluation. So let's start the general ideas like how this, for the image that is probably familiar for everyone, how does it work? So let's start with a very toy example. Let's say that you create a classifier that says that the input image is smiling or not. Playing with this knob amounts to add characteristic to the image that mimics or exaggerate the effect of smiling or other way around. What would happen if you applied on medical images? So we are going to apply it on two diseases. One is called cardiomegaly, which is the phenotypic characteristic of that is abnormal enlargement of the heart. So playing with this knob, going from one end to another end, shows like enlargement of the heart, gradual enlargement of the heart. So here, the yellow box, I'm just trying to segment the lung for you so that you know what to look at. For pleural effusion, which is another condition, the case is slightly more complicated. In pleural effusion, because of the accumulation of the fluid, the corner of the lung that is supposed to be sharp results in the blunting structure. So it's called, or gastrophenic recess, is the resulting recess. I tried my best to show that here, but if you look at it, one end of the spectrum, the lung is more sharper, and as you go toward the end, there's a recess happening toward the end of it. So this is on the visual level. So it does what you expect to do, and also in order to make sure that there is not distraction for the radiologist, they wanted to make sure, for example, some support devices such as pacemaker are preserved in the image. We modified the loss function so that like this patient-specific characteristic are preserved in the image. So here we see that in the image, the support devices on a vertebrate and also pacemaker are preserved. But what about the qualitative evaluation? So we thought about like how can we go about the quantitative evaluation. So we performed 3 levels of evaluation. The first level is that we had some criteria predefined for them. Yes.
So it's really cool results that you showed. I've read a lot about. I've seen papers where they show that if you add even some noise that's like indetectable, you can change the thing, right?
Okay.
So how do you, why are these results so different? Why is it like the direction of changing the label is actually it's like meaningful, right?
Mm-hmm.
I mean, aren't there other paths to change the label that are even imperceptible in the image?
Okay. So let me answer you short answer, and then after I'm done, because I have some slide that is not in my main slide deck, and at the end of it. Yeah. But let me give you the general idea. You're referring to adversarial attack, that is with unperceptible change in the image, that the image visual does not change. You can flip the direction. This method and adversarial attack are quite related. There is only very subtle difference that in adversarial attack, you're making changes to the X input image such that the directionality flip. There is another constraint to this method that the other conditional, which is X condition on Y, are not far from the prototypical examples. And that is the difference between adversarial attack and this method.
Oh, so you're forcing it to be in a region of the space that's kind of supported by the data?
Yes. So basically you have two conditions. You should be in, if you assume that the data lives on some sort of like a manifold, the data should still live in a manifold. Adding adversarial attack arguably take the image off the manifold, although that delta might be small. The second condition is that if you reverse the directional conditional, that like when you're doing classification, you're doing Y condition X. When you're doing generation, you're doing X condition Y. You want to create the samples that is similar to the prototypical examples of that. And the adversarial attack does not have that constraint. No. So going back to evaluation, so we have three levels of evaluation. The first level is that how much the criteria that we define for the model is satisfied by the method. The second, how much the new explanation is consistent with the clinical understanding of the disease, clinical textbook of the disease. So because these are not what we use during the method development. And finally, in my opinion, the most important part is that at the end, it's important to whom you're explaining. Is the method that you're explaining, if you run some sort of like a survey study, is convincing for the radiologists that are supposed to use this. And this is where our human computer interface HCI colleagues help us, because they are their expertise is designing the survey like this to see that how the interface of this algorithm interact with the human. So let's start with the first one. The first one was consistency. The consistency of the model with respect to black box. So x-axis for three diseases, cardiomegaly, pleural effusion, edema. On the x-axis, we are showing the desirable value of the knob, and the y-axis is generating new image, putting back to the black box. Ideally, they should follow the 45-degree. Each of these curves are initial condition of the patient. The darker the color is, so the yellowish color are more on a healthy looking condition, although no healthy person volunteered to get X-ray. And the darker is more the person that is in a different quantile of the probability. And then each different curve are initial condition of the patient. And see that regardless of the initial condition, they're all more or less following the 45-degree. There is no surprise here. This is basically saying that we wanted to be consistent with the model. It is consistent with the model, but that was part of the optimization. So no surprise. So this is more like a sanity check. The second metric, the certain sets of metric that we looked into, I'm showing you some of the results. Here is the clinical definition of the cardiomegaly. So in cardiomegaly, the radiologists usually visually look at the ratio of the heart with respect to ratio of the lung. This is so-called cardiothoracic ratio. So if the model works well, on average population, this ratio should drastically change from one end of the spectrum to the other end of the spectrum. And this is basically what this plot shows. We created the counterfactual image, and in the counterfactual image, we segmented the lung and segmented the heart, and we computed this CTR ratio, cardiothoracic ratio. And we said that when the patient is initially normal, the value reduces, and then like other way around. And this is statistically significant. And similarly for pleural effusion, we look into this blunting structure because we know that because of this accumulation of the lung, part of the accumulation of the fluid, part of the lung that this accumulation happening become blunt shape. This is curvy shape structure, while the normal looking area of the lung should be sharp. So we created external detector that we create an image, we apply this detector on it, and then we defined a score called catastrophic recess. It's basically counting the number of the time that this blunting effect is introduced in the counterfactual. And you see that regardless of the patient is starting with the normal, like a healthy looking status versus abnormal looking status, this introduction of this blunting effect is significant. As I mentioned earlier, we went through and performed a survey with the radiologists, a set of radiologists, that we showed these multiple different methods of explanation, including ours, and asked several questions. So I won't go through the detail of this question, but the general idea, I'm going to show you a summary, that basically the interface that they see was an input image with a diagnosis and comparison with no explanation, using saliency maps with explanations, methods like a GradCam, and CycleGAN that basically explain the data, and our method. And we show the saliency map, we show the animation that goes from one end of the spectrum to another spectrum, and our method that passes through this spectrum and then gradually changes from one end to another end. And the summary of the survey, I'm happy to go through the detail of that offline. That basically says, I'm going to show you two results. First, how much this type of setting helped them to understand the underlying mechanism of the black box. And here is the blues represent basically the method that we have for a specific condition called cardiomegaly. And we show that it helps them to understand much better than the other previous method. And the second one is the amount of trust that they gain as a result of providing not only diagnosis, but also explanation. And we see that the way that you convey the explanation to the user matters a lot. So, and this is one of the, I think, important components that I guess missing in the explanation is that the person that you are explaining the method to is quite important. The way that you are explaining to your colleagues as a machine learning practitioner might be different from the way that you're conveying that to a radiologist. So now, this doesn't really help us in terms of opening the content of the black box, because this just says that overall level how this method works. Can we use that to opening the black box? So I'm going to show you, in the interest of time, only the gist of the idea. This is basically, so I'm going to borrow some terminology from causal inference. So you can think of this kind of approach as, so you can think of the input image as a pill that you prescribe to a patient, and the outcome of the classifier as the outcome of that pill. Now, you can go through the two ends of this spectrum, create a counterfactual image, and look at the activation of the internal neuron. And you can correlate those internal neurons with the radiology report that comes along with images. And you can use technique from causal inference, in this specific case, mediation analysis, to identify subset of the neurons that mediate the effects of these radiology terms that are associated with the neuron into the decision making of the black box. Why is it important? Because this way you can partially open the black box and then explain the decision making of the black box, at least on a global level, into the terminology that is more familiar with the radiologist. For example, we can provide a hierarchical level of explanation that says that the neurons or set of the neurons that are responsible to detect the effect that is similar to pleural fluid first make a decision, then there is another set of neurons that fire when there is a condition called pleural vasculature prominence, and so on and so forth. And this is much more understandable for radiologists. What is that used for? Because if you are able to intervene into subset of the neurons that are mediating the effect of output, you can intervene and fix undesirable properties. For example, in this last paper that is currently under review, we showed that by putting the black box and explainer into a loop, we are able to fix overconfident black box and provide a better calibration. To summarize this part of the talk, we develop a method that provides counterfactual explanation specifically designed for radiology application. We showed that the resulting outcome, the resulting method is generate the result that is consistent with the understanding of the disease. And we are excited about the future extension of that brings the component of the causal inference into explainability that I think that they can be a fertile direction for future progress. On that note, I would like to thank the member of my groups that did basically all of the hard work for this project, and I'm just presenting, and my collaborators that make this research grounded and provide us like valuable feedback, and of course funding institution. Thank you very much.